Now let's start the next lecture again, which is on classification. And in the previous lecture, we were talking about how we can train classifiers or what kind of classifiers we have, the classical algorithms, where we discussed the max margin classifier, nearest neighbor classifier, and we also briefly looked into support vector machines. Now, there the idea was you have some algorithm which can extract like some kind of features from your data. And all those algorithms then will use those features to do the classification. All right. And of course, those features could be directly your pixel values if it's like a very small resolution image. But again, that's, you can say like that's kind of your algorithm, right? To extract features. So they assume you have features, and you can't just operate on like the spatial structure of your image. So now we are moving on to like how we can actually do classification without extracting features. We want to do this like end to end. That's like a very common term used here in deep learning, or you can say like for neural networks. So the idea is you don't separate these two steps. You just have your sample or whatever input sample you have, data you have, and you solve this jointly by extracting features and then using those features to perform classification. Okay, so that's like a very big difference between the algorithms which were discussed in the previous lecture and what we are going to study now. And of course, this is something which we have already seen. Like I think the full lecture we have already seen in the course, like in different lectures. But I think there are a couple of concepts which will be new, and I will focus more on those. And Softmax is one of those. But most of this we have already seen, so I will try to quickly skim over those slides. All right. So classification, the idea is you have, let's say, multiple classes, in this case, 2 different classes. You want a decision boundary, right? And we saw like how we can learn this in a form of equation. And that equation is just a function. Now, again, in this case as well, we are going to learn the function. But as we do so, we will actually make use of like these samples itself. Okay, so it's going to be end to end. We'll not utilize features of these samples. So let me quickly go through the framework. As I said, whatever classifier you learn, you can represent that as a function, which will make predictions given an input image. In this case, it will be your input image. Okay, so you'll have training samples, which you'll use to learn this function. Once you have learned, you will evaluate that. Okay, so the idea here is this image features and this training, it's like a single step. So you'll directly use the images, and you'll have your model which will extract features, and then those features will be used for making predictions. And the way it's done, like you have a cost function for each sample, it will tell you how good the model is doing. And then it will try to compare that with the ground truth or the label you have. And then it will penalize like your network weights. And that's how you train your model on your training samples. And once that is trained, you use that on the testing samples, and that will make predictions for you. Okay, so features, as I said, like there are a lot of different ways you can use features. But in this case, we are actually just, we're trying to learn features as we learn the classifier itself. So both of them are going to be happening together at the same time. Now, one simple way for doing that could be like you can build a neural network. You have seen this before. And what you can do is you can just transform your image to like a flattened feature vector. You did that for a programming assignment as well. And that will go as input to your neurons. And then your function is actually this transformation from neuron to neuron, how you're actually taking weighted average, or you can say linear combination of these neurons to generate future neurons, and finally to make the prediction. Okay. Then you have these convolutional neural networks. We have spent a lot of time understanding how these neural network works. So the way to use these for classification is, and that was our use case as well when we were talking about CNNs, you will take these images and you will have these convolution layers which will try to learn those filters, and those filters will extract features from your images, right? And that's basically pattern matching. It's trying to match the pattern of the kernel in the input data. And again, after a lot of such transformations, you will have like a final layer which will make prediction for you. And of course, this could be a fully connected layer, and we will see like one variation where we don't even need this fully connected layer. Okay, this is just one variation. So I think we are going to discuss one of that aspect where What if we don't have fully connected neural networks here? We just have CNNs, and can those CNN make these predictions for you? Okay, so that's a very interesting use case. All right, so the basic building block, that's these neurons. We know that it's just linear combination of your input, and these are the weights which are actually being learned. And each neuron actually predicts something, which is passed to the other neurons. And at the end, it's like the final neuron you have, which will make predictions for you. Okay, so all of this is a revision, and as we discussed in the last lecture, like if you have multiple classes, it was not that trivial for support vector machines. But in case of CNNs or neural networks, all you have to do is just add like additional neurons. So for each class, you can have a neuron, and you just use like output of that neuron as a way to estimate whether this particular class is present or not. So solving a multi-class classification problem is much easier in this case, which is a good news. And of course, like all of this is nothing. It's just transformation. It's just function, right? Function after function. And you have like composition of different functions in form of these layers, whether it's neural network or whether it's like CNNs for you. So every step, you're just transforming your data. Okay, so, and again, AlexNet, I think we spent like a sufficient amount of time understanding what this network is. So this was actually used for classification. Okay, so the idea was, given an image, it will make 1,000 predictions. So it's a n-way classification problem where n is equals to 1,000, which is like a way of saying you have 1,000 different categories in your training data. Okay, so all these parameters, I think we can skip because we already spent a lot of time in this. Now, this is, I think, one aspect which we can spend some more time now. And the idea is to make use of like just convolutional network. We don't want fully connected layers. All right, let's see how this can be done. And again, there can be a lot of different use cases why we need this. So what we'll try to do is like, first we'll try to understand how this can be done. And then we'll try to understand like how this is actually different from neural networks when we have neural networks at the end. And we'll try to understand if there's any difference in terms of number of parameters which are required in this case and in case of when you have like a neural network at the end. Okay, so let's talk about the positives here. So you know that if it's a convolutional network, you don't have to perform any flattening or something. Okay, so you will never do like you have your spatial structure, you will never lose that correspondence. You don't need any fully connected layers, which like requires a lot of parameters, which means that you will be always able to share the kernels, okay, because you're not flattening, and then whatever kernels you have, you will use the same kernel across your spatial extent of the image or of the activation maps. So let's try to understand how this can be done, and it's a very simple trick actually. And later on, you will be thinking, do we really need this? And again, it's debatable, and of course, there are like a lot of different use cases. So the trick is, what you do, you just reduce your spatial dimension to 1 cross 1. Okay? For example, let's say your input image is 28 cross 28. So far, whatever models you have designed, like for your programming assignments or whatever we have discussed in the lectures, you start with some image, then you have convolution layer, you have max pooling, you try to reduce them, but eventually you end up with like, let's say 7 cross 7 and some channels, right? And then you directly flatten from there. Now the trick is, don't flatten. Keep reducing the spatial extent. Okay, keep reducing and reduce until you reach 1 cross 1. Eventually you will reach there, right? If you keep doing convolution and max pooling. At the end, you're going to be there, like it will be just 1 cross 1. Now, once you have 1 cross 1, then again, you don't have to have like fully connected layer at the end. For 1 cross 1 feature map, what you can do is you can actually use a convolution whose shape is 1 cross 1. Okay, so it will be like it will be just one value. And of course, like it will have some depth depending upon how many channels you have. And so again, you can perform that convolution operation on that 1 cross 1 activation map. If you think about that in more depth, that's exactly what you do in your fully connected networks as well. Okay, so the operation is actually not different, but still conceptually you can define this as like a convolution network. Okay, so it is fully connected layer because let me actually quickly describe. I think it will be useful. So let's say you start with some resolution 28 cross 28, and let's say 3 channels. And at the end, you have a lot of convolutions, a lot of max pooling layers. You reach to 1 cross 1 and some number of channels. We don't care like how many channels you have. Then what will happen if you try to flatten this? So this is one way. Then you will get C features out of this, right? That's what like flattening does. It just take like all the activation values and create like a linear vector. The second way could be you don't flatten and you still have like 1 cross C. Now you have C values, and let's say you want to add a fully connected layer to make 1,000 predictions. So you will have 1,000 different neurons, and you will have 1,000 times C weights here, right? In this case, what you do, you have a 1 cross 1 kernel, and you know that depth of that kernel should be C, right? Because you are applying kernel, because you know that it should match like the depth of your activation map. And to make 1,000 predictions, you need 1,000 different kernels, right? So this will just give you one value. So you need 1,000 such kernels. And at the end, if you think about, this is exactly like your fully connected layer, because in convolution, what you do is you just take linear combination across your depth. That's how your convolution kernel works, right? And the same operation is actually performed when you have a fully connected layer, where for every neuron, you compute linear combination of all the neurons in the input layer. And you do that 1,000 times for 1,000 different neurons. So basically the mathematical operation which is happening is exactly the same, but it's just like a different way of representation. Okay, so I will tell you like why this is very, very useful and what is the actual use case here. Of course, you can use this for classification as well, but there are like more interesting aspects where this plays a very, very important role. Okay, so this is like one simple example. So you have CNN fully connected, so you'll have to flatten it, and finally you are getting, let's say, 4 different values. So what is happening at this point, you will have to flatten this volume. So you will have a feature vector which has 5 cross 5 cross 16 different values, which will be connected to 400 different neurons. Now, to convert this to a fully convolution network, what you can do is, so this part is not going to change. You can still apply like a 5 cross 5 kernel on this. And if you do that, then you will be only able to apply that kernel once at the center of this, right? Because the resolution is 5 cross 5. And then you will use 400 such kernels to get 400 different values. And then you can have 1 cross 1 kernel. Again, it will give you something like this. And again, you can have like 4 different kernels, which will provide you like 4 different values, which you can use as prediction. So both are doing classification, and both have almost similar structure. The only difference is in this case, you are using fully connected layers at the end. And in this case, you don't have fully connected layers. It's completely convolutional. Okay, so let's talk about the use case of this. Now, convolution, you know that once you have learned this model, then it doesn't matter like what is the input size of your image. Okay, and again, think about this. So in this case, it's 14 cross 14 cross 3. Now, what will happen if instead of 14 cross 14 cross 3, I use a much bigger image? Let's say 28 cross 28 cross 3. Whatever model or network you have trained, you will still be able to use that. And the reason is, whatever kernels you have 5 cross 5 over here, you will still be able to apply those kernels on the input image. It's just you will apply at more locations. And that's only going to change like the shape of this feature volume here. It might go to like, instead of 10 cross 10, it might go to maybe 25 cross 25 or 26 cross 26, right? And still you'll be able to perform this max pooling operation. The only thing is going to happen is the spatial resolution will change. It might not be 1 cross 1. It might be, let's say, 4 cross 4 or 6 cross 6. And still the same weights, same network will work. And at the end, what is going to happen is, instead of getting like 1 cross 1 cross 4, you will get like some spatial resolution as well. It's a 4 cross 4 cross 4. And it's up to you how you want to use that. You can either just do average pooling of that. And again, you can get your 4 predictions if you want to use like this kind of architecture for classification. So what it's doing is, during test time, let's say if you have a bigger image, even without resizing, you will be able to do this network on that bigger image and be able to make predictions. Okay, so that's one use case. Now, the more interesting use case for this fully connected network is, if you think about like the programming assignment you have, the third programming assignment, where we're asking you to build an autoencoder. Now, in that case, if you don't have fully connected layers in between in the bottleneck, you just keep it fully convolutional. So you will see that if you train your autoencoder network, which is fully convolutional, in let's say a very small resolution image 28 cross 28, you will still be able to use the same network on an image which is, let's say, 500 cross 500, right? And still, like, let's say if you're doing autoencoding, you will be able to do autoencoding on the bigger image as well. If you are doing colorization, you will be able to colorize the bigger image as well. Okay, so that's, I think, a very interesting use case, and that's autoencoder is one example. But I think where it's applicable, if you try to bring all those problems under a single umbrella, you can say it's kind of a dense prediction task. And later in the course, we will look into some of those problems. So one of the dense prediction tasks is, let's say, image segmentation, where given an image, for each pixel, if you need some kind of prediction. Okay, so that you can say is a dense prediction task. And in that case, if you use like a fully convolutional network, then you can change the resolution of your images no matter what, but still you will be able to use the same network to make predictions on that varying like images with varying resolution. Okay, so that's a very, very interesting use case of this. But of course, you can use it for classification as well as we discussed. So that was one aspect, and I think the other aspect I wanted to discuss is like what's the very critical idea when you build like a classifier using CNNs. We'll spend some time there, but before that, we have, I think, how you can introduce non-linearities. I think we have covered this aspect, and we know that we need activation functions after every layer. And if you don't do that, it doesn't matter you have 10 layers or 1,000 layers. It will all just compress to a single function. Okay, so that will be equivalent to having a single layer. And that's why we need these nonlinear activation functions in between. And so, for example, like the sigmoid activation function is very popular, which can be used. What it does is it flattens or normalizes your values between 0 and 1. Okay, and because this function is nonlinear, then the transformation is nonlinear. And if you do that like after every layer, then that's actually making the network capable of learning complex functions with minimal number of parameters. Okay, so sigmoid was one. Then we have some other variations as well. We have tanh, we have ReLU. And again, it depends like what kind of use case you have. So the intermediate layers, more or less, it doesn't matter actually. You can try different activation functions. Again, ReLU is a very interesting one, which works pretty well. One very interesting aspect of this activation function is, what if you are going to use them on your final prediction? And then there it actually matters which activation function you want to use. All right. So for example, if you want to make prediction about some objects, let's say it's a classification problem, then having a ReLU activation at the end, it won't make that sense, because what it's doing is it's giving you values between 0 and infinity. So if you have a prediction value between 0 and infinity, it will be very hard to interpret like those values. Okay. For example, let's say if you get a value of 10, you can say, okay, 10 seems like a positive number, so this class might be present. But what if like in the next run you get like a value of 1,000? Then how will you compare those two? And in the next, if you get, let's say, 100,000, so compared to 100,000, 10 is nothing, right? So in that sense, ReLU might not be that useful. So in that case, sigmoid might be useful because it's actually bringing them between 0 and 1. So then it's kind of normalized. So you can say that if it's closer to 1, it seems like positive. Closer to 0 seems like negative. And if it's like, let's say 0.5, then it's kind of confused. Okay, so then sigmoid might be a good activation function there. And now tanh has, again, very interesting use case there. If you, let's say, are trying to solve a binary classifier, all right? And in binary classifier, you don't want to use 2 neurons. Let's say you just want to use 1 neuron. And again, of course, you can use sigmoid for that as well, but tanh could be pretty interesting because what it will do is for one class, it might predict negative values. And for one class, it might predict positive values. So it will be pretty easy for you. You can just check like the sign of the value, what the network is predicting, and that will tell you the class. And of course, you can do that for sigmoid as well. You can argue that, okay, what if I just like use 0.5 as a threshold? And if it's greater than 0.5, it's a positive, otherwise it's a negative. And that's entirely true. You can of course do that. But if you look at if you look at like these curves carefully, the non-linearities in these two is slightly different. So that will make a difference and it might affect like the performance you have. And again, it's very hard to say that which of these will be better. You'll have to test and try that out. Okay, so yeah, I think we covered these points. So this is also good. We know like if it's a binary classifier, you can use single output or you can have 2 outputs. And for multiclass, you can have multiple neurons, which will make predictions. Now, as I said, we have just like mainly 2 concepts which are very interesting in this lecture. The first one, I think we discussed how to convert your networks to fully convolutional. That has a lot of applications. The second aspect is softmax activation. Okay, so pay close attention to this. This is a very, very interesting concept. Now, the idea here is whatever prediction your network is making, we actually want them to be a little interpretable. For example, like the earlier scenario I shared, like let's say if you're using a ReLU activation, so it's very hard to compare like values of 10 versus 1,000 or 10 versus 100,000. Okay. So what Softmax does is, again, it's activation function, and it tries to turn your network predictions into probabilities. Okay, and it's very powerful actually. So the way it does that, it will take whatever network predictions you have, and one thing it will do is it will scale it between 0 and 1. So that's like the basic rule, right? Because the probabilities cannot be negative and your probabilities cannot be greater than 1. The maximum probability you can have is 1. So what it will do is it will try to normalize the values between 0 and 1. And the way it does is it's not just scaling. Of course, you can just put a sigmoid and it will give you 0 and 1. What it does is it tries to take into account like different magnitudes of the classes you have. For example, if you have 3 different classes, it will look at all the 3 classes at once. And that's the difference between sigmoid. Sigmoid will not be able to do that. So what sigmoid will do is it will look at 3.2, and then maybe you will have some kind of upper threshold, right? And then it will directly convert this to like 0 and 1 without looking at this 5.1. Okay, but Softmax, when it's trying to convert this to probability, it will also look at this particular value. Now let's see how that's done. And this is like a very simple Softmax activation function. If you look carefully, it's a very simple function. What it's trying to do is it is first trying to compute the exponent of all the predictions. So E is for exponent, and Sk is like for the prediction of the network for kth class. All right. And in the denominator, you have summation. Okay, so this is summation over all the classes. And again, what you are summing up the exponent of all the predictions. Okay, so then the basic step should be, what you need is you need exponent of all the predictions, right? So let's do that. If these 3 are your network predictions and this was a cat, but your network predicts like 3.2, 5.1, negative 1.7. I mean, how can I interpret this? I mean, I don't know. This is a negative value, so I can say, okay, frog is not present. This is like 5.1, seems like positive, so car could be present, right? But then cat is also 3.2. So of course, the network is making error. It's kind of because this is the maximum one, and the network is saying this is a car. But then there is no way of telling that, like how good the network is doing, right? I mean, I can't tell whether 3.2 is pretty bad or it's like maybe pretty close. So that's what like Softmax will help in solving for us. The first step, you compute the exponent because we need that. Okay, so you just compute the exponent values. All right. Second step is you need like summation of all this for the denominator. Right? So you can just add these values, which is fine. It will give you something like maybe 190 or odd, that number, right? And then what you do is once you have that number, for each class, whatever exponent you have, you just divide with that number. So in this case, it will be 24 over that 190. And that will give you 0.13. And again, this will be 164 over 190. Going to give you this. And this is going to be 18 over that number. So pretty close to 0. And these are actual probabilities. Okay, so there are like some interesting properties here. You can easily say that, okay, the confidence score of this prediction for this image being car is 87%. And that I can interpret. Okay, 87%, that seems like a very high number. And the probability of this image of being for a cat is just 13%, and which I can easily interpret 13% is pretty bad, right? So I have like some sense of how good the network is doing. And this is completely 0. Negative was not, I mean, I can't say like how good or bad this is, but 0 I know. So frog is definitely not present. Okay, so that's like one thing. The other thing is these are probabilities. So what should happen if you sum up all these? It should give you exactly 1. So you can do that. It's equal to 1, right? And that's because like the equation you're using. And that's how probability works, because then you can't have probability of 1 like if you sum all of those and then everything is normalized. Okay, so that I think is a very interesting concept. And if you have to solve like a single level classification and you have a lot of classes, you should always use Softmax, okay, to train your network. This should be the final layer in your network always. It will help you like in training your network much better. And also it will give you some kind of interpretability. Now, again, I mean, we have good things, but again, nothing is like a pure gold, right? So what if we have multi-labels? Then this is not going to work. Because if you have multiple labels, then first of all, your sum of probabilities for like all the classes cannot be 1. Because you can have both cat and car present in the same image. And if that's the case, then this will have probability 1, this will have probability 1, this might be 0. So that will sum up to 2, right? And that's not right. And sadly, that's the case. If you have multi-label classification problem, you should never use Softmax. It won't work. And the simple trick is use sigmoid activation. Okay. And what sigmoid will do is it will independently normalize your network predictions between 0 and 1. And which is fine, because for multi-level, we don't care about like normalizing across classes. And the reason is multiple classes can be active at the same time. So still we will be able to interpret those values pretty well. All right, so that's good. Then loss function, I think we have already discussed. Cross entropy is a pretty good loss function to use for classification. And this is a very general formulation for a loss function where this is your input data, network weights, and this is going to give you network prediction. And your loss function is just going to compare that network prediction with the ground truth. Okay, so for classification, usually a cross entropy loss is pretty powerful. And this formulation, again, I think we have discussed already in this course. I have explained like why this cross entropy works for classification. Okay, I think ran through some of the trivial corner cases. And then that's all you need, right? You have a loss function, then you just train with gradient descent. And of course, for training, you have a lot of optimization algorithms. So you should not worry about this, because again, this is like these are advanced topics. And for a course project, even for a programming assignment, you can just pick any one of these. Even if you use SGD, that's perfectly fine. But the good thing is, like what are the different parameters you need for your optimizer, right? Like the learning rate or the decay and the momentum, all those things. And at the end, like if you have a CNN, you know that what you're learning, you are actually learning those kernels. And those kernels are, again, just trying to find that kind of pattern in the input images. And that's all what is happening. And everywhere it's filtering is happening, right? Basically, like the core operation is filtering. And the only question is what exactly we are filtering. In the initial layers, we might be just filtering these like basic shapes, these edges, right? Or color patches. And in the deeper layers, we might be filtering these complex shapes. And at the end, depending upon if you are able to find this pattern or not, the network will make its predictions.